Hello everyone. This lecture is about curve sketching of rational functions. So we have a rational function here. It's 1 over x squared minus 6x plus 8, and we want to draw the graph of this rational function. So the first thing we perhaps do is to find the domain of the function. We want to know where this function is defined, where it's not defined. If you don't know the domain of a function, how do you want to draw its graph? So if you don't know over what interval a function is defined, or for what values of x is it defined, for what values of x is it not defined, if you don't know all this information, how do you want to draw the graph? So we're going to factor the denominator first of all. So y equals, so it's going to be x minus 4, x minus 2, okay? Two numbers add up to -6, product positive 8. It's going to be -2 and -4. And obviously the roots of the denominator are where the function is not defined. So if x is 2 or if x is 4, 1 divided by 0 would be undefined. So we're going to say the domain of the function is all set of real numbers such that x can be any number except 2 and except 4. It cannot be 2, it cannot be 4. So that's the domain of the function. Okay, next thing, we go after finding the asymptotes. So to find the vertical asymptotes, we are going to set the denominator equal to 0. And obviously there's two factors in the denominator. If x minus 4 is 0, it gives you x equals 4. If x minus 2 is 0, it gives you x equals 2, which are representing the two vertical asymptotes. Okay. Horizontal asymptote, we see that the top is a constant. It's a 0 degree polynomial function, you can say. And the denominator is quadratic. So because the degree of the top is less than the degree of the bottom, so we do have a horizontal asymptote, which is actually the x-axis. So for the horizontal asymptote, we have y equals 0, which is the equation of the x-axis. So we have our asymptotes, the two vertical asymptotes, 2 and 4, and then this is the third one, which is a horizontal asymptote. It is actually the x-axis whose equation is y equals 0, clearly. So I'm going to label it. So that's y equals 0, the horizontal asymptote. Next thing we're going to take care of is finding x-intercepts, y-intercepts. So I'm going to set x equal to 0. So I get y equals 1 over 8. So this becomes my y-intercept. So I know that the graph must intersect the y-axis at 1 over 8, somewhere here. This is the y-intercept. You find it always by setting x equal to 0. And then if you set y equal to 0, you see that it's impossible because 1 over that denominator is never ever equal to 0 because the numerator is 1. How can 1 be equal to 0? And the message it has is that there is no x-intercept. That's the meaning of it. So I know that the graph I'm supposed to be drawing later on, it is not going to intersect the x-axis. So I know all these pieces of information. Okay, so we did an intercept analysis, we did an asymptote analysis here, and we did a domain analysis here. Okay, next thing, we want to know the behavior of the graph at the neighborhood of its two vertical asymptotes. So for example here, when x approaches 2, so x approaches 2 from left-hand side. So that's the symbol we use in calculus. We put a little negative sign on top. This doesn't mean that the number 2 is negative. It means that x is approaching 2 from left-hand side. And if you write x approaches 2, put a plus sign on top, right corner, it means that x approaches 2 from right-hand side. So if x approaches 2 from left-hand side, let's say it's like 1.99, for example, okay, or 1.999, okay. If that is the case, let's see what happens to y. So if x approaches 2 from left-hand side, then what happens to y? Okay, so let's have a look. So the numerator is 1, that's etched in stone, you can't change it. But if x is 1.99, this factor is negative. This factor is, again, negative. So negative times negative is positive. So the outcome is going to be a positive value. But the thing is that because the denominator is very close to 0, because 1.99 minus 2 would be like negative 0.01. Now, if I pick x to be extremely close to 2, such as 1.999999999, in that case, the denominator will be very close to 0. For example, it would be 0.000000001, okay, with a negative sign outside. So when you're dividing 1 by a number that is extremely close to 0, the outcome is extremely large. In other words, we say that y approaches positive infinity. Okay? So if x approaches 2 from left-hand side, y approaches positive infinity. It means that the graph has this kind of behavior. So on the left-hand side of the vertical asymptote x equals 2, the graph is approaching positive infinity as x approaches 2 from left-hand side. So if x approaches 2 from right-hand side, so then we can select the value such as 2.001. And when you plug in 2.001, this factor becomes positive. That is negative. Positive times negative is negative, and 1 divided by a negative number is going to be negative. So that means that y would approach negative infinity, because think about it. This factor here, 2.001, could have been 2.000000001. And then minus 2, it would be like a very small number close to 0. So always bear this in mind. So y would approach infinity because the denominator becomes extremely small, causing the whole fraction to become extremely large. This is so logical. So that means that on the right-hand side of the vertical asymptote x equals 2, the graph behaves like this. It is on the right-hand side, and y approaches negative infinity. So this is the behavior of the graph at the neighborhood of its vertical asymptote. But then we have two vertical asymptotes, so we need to know what is happening in the neighborhood of the second vertical asymptote, whose equation is x equals 4. So for that, we're going to perform another analysis. We're going to say if x approaches 4 from left-hand side or from right-hand side, then what is happening to y? So this time, x approaches 4 from left-hand side. We can pick something like 3.99. So 3.99 here will make this negative. That's positive. So we end up with negative infinity with a similar analysis. I suggest you review what I said before a couple of times. And then x approaches 4 from right-hand side. It could be like 4.001. Plug in here. That's positive. So we end up with positive infinity. So on the left side of 4, we have negative infinity. So it's like this. And then on the right side, we have the graph that is above the x-axis. So this will be the behavior. Okay, we don't have any x-intercept, as I said, but we do have a y-intercept. So when this graph goes down on the left, it has to come and cross the y-axis, obviously. And then as x approaches negative infinity, as x becomes extremely small, so that's what happens to the whole fraction. Imagine x is like negative 10 million. When you plug in negative 10 million here squared, it becomes like positive. And then when you do the math, you end up with a huge number in the denominator, but 1 divided by that huge denominator will be very close to 0, but still a positive number. So this way we know that when this graph goes down just like this, it intersects the y-intercept, and then as x decreases on the left-hand side, the graph becomes closer and closer to the x-axis, but never touches it, because we said that there is no x-intercept, okay? But the graph becomes extremely close to the x-axis on the left-hand side as x approaches negative infinity. On the right side, what happens? Instead of x, you can plug in like 10 million. See what happens. So 1 over 10 million squared minus 6 times 10 million plus 8 would be like a very, very small number close to 0. And it would still be a positive number. Sometimes it's a negative number, which means that the graph approaches the x-axis from below. But here we got positive in both cases, which means that the graph approaches x-axis from above. So the graph is going to be something like this. So as x approaches infinity, y or the graph approaches 0. And in the middle, when x equals, let's say 3, roughly, you plug in 3, with 3 squared, which is 9, 9 and 8 is like 17, 17 minus 3 times 8, that's 17 minus 18, it's going to be -1. So we end up with -1 as the number here when x is 3. So the graph obviously goes up and then it goes back down because of the end behavior, not end behavior, because of the behavior of the graph at the vicinity of its vertical asymptotes. So it has to go up, but it's not going to continue crossing the x-axis. We said you don't have any x-intercept. So it's going to come back down. And this is going to be the general sketch of this rational function. You may plot this point a little bit higher, a little bit lower. You know, the curvatures could be like thinner or wider. Those things, those details that we're not that much interested. We just want to know how the graph looks like in terms of its general shape. With regards to the range, if we knew this is truly the maximum, then we could say the range is like above the x-axis and below -1. But we cannot say that because we don't exactly know if this maximum point is having a y-coordinate of -1 or -0.99 or like -1.1. So to draw it more accurately, we need more tools, and we're going to learn that in calculus. But so far, this much, I would say it's good enough for us to draw a sketch of these rational functions. I suggest you practice graphing rational functions so that you become better and better at it. Thank you.